Hello everyone, today I will be presenting a tutorial on QUIC, a modern transport protocol designed to improve the web performance. So in this presentation, I will first introduce QUIC and discuss the limitations of TCP. Then I will explain how QUIC addresses these issues, followed by a demonstration using Wireshark. So first, let's start with an introduction to QUIC. QUIC, which stands for Quick UDP Internet Connections, is a modern transport protocol developed by Google. It is designed to improve the performance of web applications and is widely used in HTTP3. Unlike traditional protocols such as TCP, QUIC runs on top of UDP. This allows it to reduce latency and provide faster connection establishment. QUIC integrates both transport and security features into a single protocol. This means it can establish secure connections more efficiently compared to the traditional TCP and TLS combination. However, traditional TCP has several limitations that affect performance. First, TCP requires a three-way handshake before any data can be transmitted. After that, a separate TLS handshake is needed for encryption. This increases connection setup time and latency. Secondly, TCP suffers from head-of-line blocking. This means if one packet is lost, all subsequent packets must wait, even if they're independent. Finally, TCP cannot efficiently handle network chaining. For example, if a user switches from Wi-Fi to mobile data, like 4G or 5G, the connection may be interrupted. So these limitations motivate the development of QUIC. So QUIC was designed to address the issues and improve overall network performance. First, QUIC provides faster connection set up using an RTT handshake and even zero RTT for returning connections. This significantly reduces latency compared to TCP. Secondly, QUIC eliminates head-of-line blocking by using multiple independent streams. This means packet loss in one stream does not affect others. Third, QUIC has a built-in encryption using TLS 1.3, so there is no need for a separate security layer. Finally, QUIC supports connection migrations using connection IDs instead of IP addresses. This allows the connection to continue even when the network changes. Overall, QUIC offers a faster, more secure, and more flexible alternative to TCP. Now that we have discussed the key concepts and advantages of QUIC, let's look at how it works in practice using Wireshark. So the purpose of this demo is to capture and analyze real QUIC traffic over HTTP3 using Wireshark. So first I will clear the cache of the Microsoft Edge for a more precise output. So I will open Wireshark. Yeah, I'm capturing network traffic using Wireshark on the Wi-Fi interface. Then I use a filter QUIC to focus on the QUIC traffic. Okay, so I will reopen the Edge and then visit YouTube. I will click on maybe a random video. And I will stop captioning. So now we can see that multiple QUIC packets capture over the port 443, which confirm that the HTTP2 is being used. So now I will expand a structure, a QUIC packet. So yeah, we are looking at the Quick packet capture in Wireshark. Right. This section shows show the Quick protocol details. So first of all, this one, the header form. This indicates a long header, which is used during the initial handshake phase of Quick. Next, we have the packet type. This is an initial packet, meaning it's a part of the connection establishment process, and it replaces the TCP SYN and the TLS client header in the normal and the traditional TCP TLS connection. This one is the this one is the version. It shows the quick versions being used. This is the destination connection ID, which identifies the connection instead of using IP and port. This allows connection migration. And below here is the source connection ID. But in this packet is not being used. The token is used for validation and security during the handshake process. And the packet number, the packet number used for ordering and reliability. And down here is all the data frames. So for example, the crypto frame carries the TOS handshake data inside the Quick. This shows that the Quick integrate the TLS directly into the protocol. So as you can see here, we have some handshake packets, where the client and the server exchange encryption keys. And inside the initial packet, we can observe different Quick frames such as crypto, padding, ping, and there are also some more as ICK. So after the handshake, all packets are encrypted and appear as protected payload. This shows that we integrate security directly into the transport layer. So now that we have observed real quick traffic in Wireshark, let's return to the slide and compare Quick and TCP. So the figure above demonstrates the differences in connection establishment between TCP, TCP-TLS, and Quick. In TCP, three-way handshake is required before any data can be transmitted. This involves the SYN, ACK, and ACK package, which already introduce latency. When TLS is added, an additional handshake is required for encryption, further increasing the delay. As you can see, we have also the TLS client, TLS server, TLS in and line request. But in contrast, Quick combines both transport and security handshakes into a single process. It can establish a secure connection in just one round trip, known as the one RTT. For returning connections, Quick can even use the zero RTT, allowing data to be sent immediately without waiting. Overall, Quick significantly reduced connection setup time compared to TCP. Move to the next slide. This table summarizes the key differences between TCP and Quick across several important features. First, TCP operates over its own transport protocol, the TCP and the IP, while QUIC runs on top of the UDP. This allows QUIC to be more flexible and faster to deploy. In terms of handshake, TCP requires a three-way handshake and a separate TLS setup, which is more slower, whereas QUIC uses a faster 1 RTT or even 0 RTT handshake. For security, TCP relies on external TLS, while QUIC integrates encryption directly using TLS 1.3. TCP suffers from head-of-line blocking, meaning one lost packet delays others, while QUIC avoids this using independent streams. QUIC also supports multiplexing and connection migration, which TCP does not handle it efficiently. Finally, although both protocols provide reliability and congestion control, QUIC generally achieves better performance due to reduced latency and improved data handling. In conclusion, QUIC significantly improves the performance and efficiency of modern internet communication. It reduces connection latency through faster handshakes, including 1 RTT and 0 RTT. It also eliminates head-of-line blocking by using independent streams, allowing data to be delivered more efficiently. In addition, QUIC integrates encryption directly into the protocol using TLS 1.3, ensuring secure communication by default. Features such as connection migration make QUIC more suitable for modern mobile networks. Overall, QUIC provides a faster, more secure, and more flexible alternative to TCP, and it plays a key role in the adoption of HTTP 3. So that's all for the quick tutorial. Thank you for listening.